Hello and welcome to The Explainer. Today we're diving deep. We're going to peel back the curtain on reality itself and take a look at the fundamental rules that govern our entire universe.
You know, have you ever just had that feeling that there's more to reality than what we see? That underneath everything there are these invisible, powerful laws pulling the strings? Well, guess what? You're absolutely right. So that's what we're doing today. We're going on a journey to uncover those hidden rules. We're counting down the 10 most important effects in physics. And each one is like a little clue, a breadcrumb, that reveals a universe that is way, way stranger and more connected than you could ever imagine.
Okay, so we're starting our countdown in a section I kind of like to call the cosmic and the strange. We'll kick things off with something you've definitely experienced before. And then we'll move into stuff that really starts to challenge, our whole definition of reality.
All right, let's get static.
Kicking us off at number 10, we have the Doppler effect. And you already know this one, even if you don't know the name. Just think about an ambulance siren. As it comes toward you, the pitch is super high, right? And then as it passes and goes away, the pitch drops. That change in pitch, that is the Doppler effect.
It's really all about relative motion. When something making a wave, sound, light, whatever, is moving towards you, those waves get all bunched up. So the frequency seems higher. And when it's moving away, the waves get stretched out, and the frequency seems lower. And this isn't just for sound, by the way. It works for light, too, which is huge. It's actually how astronomers can tell that distant galaxies are racing away from us, which is one of the key pieces of evidence that our universe is expanding.
All right, on to number 9.
Okay, at number 9, the butterfly effect. Now, we've all heard the phrase, right? A butterfly flaps its wings in Brazil and sets off a tornado in Texas. But the scientist who came up with it, Edward Lorenz, he was actually making a much deeper point. It's not just that small changes have big effects. He showed that for really complex systems, like the weather, there is a fundamental limit to how well we can predict them. It's basically a lesson in humility, straight from chaos theory.
Coming in at number 8. Number 8 is the Meissner-Ochsenfeld effect. And let me tell you, this one is just pure visual magic. So a superconductor, when you get it really cold, doesn't just have zero electrical resistance, it also actively pushes out magnetic fields. What does that mean? It means if you put a superconductor on top of a magnet, it just floats. It hovers right there in midair. We're talking real-world levitation, no Jedi mind tricks needed.
All right, let's look at number 7.
Okay, number 7 is the Aharonov-Bohm effect. I know, it sounds super abstract, but stick with me, because this one is a serious mind-bender. For the longest time, physicists used this mathematical shortcut called potential to help describe magnetic fields. They thought it was just, a handy tool, not something real. Well, this effect proved them wrong. It showed that a particle can actually be affected by this potential, even in a region where the magnetic field itself is zero. So the big takeaway here is that this potential isn't just some math trick. It's a real physical part of our universe.
And that brings us to our next section. Let's call this one Motion, Magnets, and Mass. Here we're going to dig into the surprising rules that govern how things move, the super strange ways matter behaves in magnetic fields, and the bizarre nature of the most massive objects in the entire cosmos.
Let's do it. On to number 6.
Coming in hot at number 6 is the tennis racket effect. And this is one you can actually try at home, carefully, with a book or even your phone. If you toss an object so it's spinning along its shortest axis, it's totally stable. If you spin it along its longest axis, also stable. But if you try to spin it along that middle or intermediate axis, it just chaotically flips over every time. It's this really beautiful and totally surprising consequence of the physics of how things rotate.
All right, we're halfway there. Number 5. At our halfway point, number 5, we have the Hall effect. So picture this. You've got electricity flowing through a thin, flat piece of metal. Now, if you bring a magnet nearby, that magnetic field actually pushes the moving electrons over to one side of the plate. This buildup of electrons creates a tiny voltage you can measure across the plate. And because that voltage is directly proportional to how strong the magnetic field is, it's an absolutely brilliant way to build sensors that detect magnetic fields.
And now for number 4. For number 4, we're heading out to the very edge of spacetime with the Hawking effect.
Stephen Hawking completely flipped our understanding of black holes on its head. He showed that because of quantum effects right at their event horizon, black holes aren't actually truly black. They emit this incredibly faint thermal glow. We call it Hawking radiation, which means that over immense, almost unimaginable amounts of time, they can actually evaporate and just disappear.
And now, it's time for the grand finale. We are heading straight into the quantum realm for our top 3. These are the big ones. The effects that completely tore up the old rulebook and showed us a reality at the smallest scales that is probabilistic, deeply interconnected, and frankly, just downright bizarre.
Let's do it. Kicking off the top 3. In the bronze medal spot, at number 3, is the photoelectric effect. This is the discovery that pretty much kicked off all of quantum mechanics. Here was the puzzle that was stumping everyone. If you shined a low-frequency light, like red light, on a piece of metal, nothing happened. It didn't matter how bright you made it. But if you used a high-frequency light, like blue or UV light, it would knock electrons right out of the metal, instantly, even if the light was super dim. It was Albert Einstein who cracked it. He suggested that light isn't a continuous wave, but is actually made of little, discrete packets of energy he called photons. And with that one idea, he blew the door wide open to the entire quantum world.
Okay, our runner-up, number 2. So for number 2, our runner-up, I have a little riddle for you. Imagine you have 2 perfectly smooth metal plates. They have no electrical charge, and you place them in a perfect vacuum, total emptiness. So why do they attract each other? This is the Casimir effect. It turns out that a vacuum isn't really empty at all. It's constantly fizzing with these virtual particles that pop in and out of existence. And there's more space for these particles to pop up outside the plates than between them, so you get more pressure from the outside pushing them together. It's literally a force created from nothing. And now, the moment we've been waiting for. The number 1 most important effect in physics.
And that brings us to our number 1 spot. In my opinion, the most fundamental and mind-blowing effect in all of physics, quantum tunneling. Think about it. In our everyday world, if you throw a ball at a wall and it doesn't have enough energy to go over it, it just bounces back, right? You're stuck. But in the quantum world, it's different. A quantum particle can essentially leak right through a barrier it doesn't have the energy to overcome. There is a non-zero chance it will just appear on the other side. This isn't science fiction. This is real. It's literally the reason our sun works, the reason it can fuse atoms together and shine. Wow. Okay. So after that whirlwind tour, what's the big picture? What have we actually learned? Well, for one thing, the universe is absolutely not the nice, neat clockwork machine that people once thought it was.
I think the biggest takeaway is that reality is just subtle, and it's strange. What we even mean by words like particle or vacuum can actually change, depending on our perspective and how we're moving. Things that seem totally impossible, like tunneling through a solid barrier, are not only possible, they happen all the time at the quantum level. And ideas we were sure were just handy math tricks, like that electromagnetic potential, well, they turn out to be physically real. Our universe is governed by a set of rules that are deeply interconnected and truly, truly non-intuitive.
And that just leaves us with one final thought to chew on. Every single one of these effects, when it was discovered, was a total surprise. It was a crack in the old way of thinking that opened up a whole new, deeper level of understanding. So, if these are the incredible, mind-bending rules we've already managed to figure out, just imagine, what else is still out there waiting for us to discover? Thanks for joining me.